Swayam Prabha. Digital India. Educated India.
Good morning everybody. Today I will try to discuss another module of advances in laser, welding and joining technologies. So this module is the computational welding mechanics. Actually in this module we will try to focus on the different but very simple mathematical calculation normally follow in the welding processes. So, there are if you look into the welding mechanics, that a lot of subject actually involved in this welding process. For example, from heat transfer to fluid flow, even at the same time electromagnetic field also generated during the welding process, and finally there is some stress analysis, then residual stress is also generated during the welding process. So, there is a wide range of area actually covers this module, and that is computational welding mechanics. If you look into the subsection of this module, the first will focus on the analysis of the heat flow in the welding process, then how to estimate the cooling rates, and because we have already discussed that what is the influence of cooling rate in the microstructural changes in the welding process, or maybe how cooling rate affects in the solidification process of the welding. That three we will cover in the welding metallurgy section, but here we will try to focus only for the mathematical calculation or estimation of the different parameters that actually very significant in the welding process. Then we will try to look into the models of the welding heat sources, because how to represent the heat sources from the different source used in the welding process, for example, arc, laser, electron beam. So, all these cases the representation of the heat source in the mathematical form are different. So, that will try to focus on the how to do that kind of heat source modeling. Then I will try to focus on that analytical solution of the temperature distribution, and then analytically how you can estimate the temperature within the weld zone, because this temperature distribution is important, because we can use this distribution of the temperature and we can estimate the cooling rate from temperature distribution, and finally we can correlate this cooling rate and microstructure. So, in that sense we need to understand the correct estimation or distribution of the temperature and in the welding process. Then heat transfer mechanism, and if you try to apart from the analytical solution, what are the other numerical solution can also develop in the welding process to for the solution of the temperature distribution, fluid flow, and that means material flow within the weld pool, and then amount of the residual stress or distortion level at the final weld structure. So, that kind of coverage also there. Then we will be look into that influence of the surface active elements, because this phenomena is very significant. Theoretically that we already described what is the importance of the surface active elements in the welding process, but mathematically how we can take care of this apex of the surface active elements in the mathematical modeling of the welding process, that we will try to discuss in this module. And then finally, what is the amount of the residual stress will be generated, or what is the amount of the distortion will be generated in the final weld joint. That is very much significant for the designing of the any component, or when you try to fit the one component with respect to the other component. This distortion level and residual is very significant, and residual stress is important to know the service life of the weld joint. So, in that respect, all these phenomena is possible to estimate mathematically, and that is the focus of this module. So, before doing that, let us try to understand what are the physical aspects involved in the welding process. So, let us take an example here, that this example shows that there is a heat source. So, that heat source comes from the laser or some electric arc or some electron beam, or due to resistance heating as well. So, with the application of the heat source, there is a certain zone localized area, the melting happens, and the surrounding area also, that is the heat affected zone. So, some development temperature above the base material, above the ambient temperature. So, with the advancement of the, at the same time with the advancement of the heat source, the subsequently part is solidified, and then apart from the solidification zone, certain part is the heat affected zone. Here we can see the different zone, the melt pool, solidified zone and the heat affected zone from the figure itself. So, this is the typical characteristic. So, if we see the physical aspect point of view, here you see there is a application of the heat flux from the heat source, the localized melting and solidification, and within this molten pool there is a flow of the molten material. So, we often neglect the flow of the molten material, but that having some importance also, we will discuss this one. And then finally, what happens, there is this variation of the temperature distributions brings some differential thermal expansion and contraction, and that thermal expansion and contraction actually leads to the formation of the residual stress and distortion in the weld structure. And that structural changes, that due to the effect of the heat, the structural changes comes from the solidification behavior in the welded structure. So, all these phenomena actually involved in case of this we are talking about the fusion welding process. Now, other aspects also, if we see the physical aspects of the welding process, when there is involved in the metal transfer from the consumable electrode also. Here we can see the droplet transfer, but along with the droplet transfer, we can, in the mathematical sense, we can say that within the domain there is a mass transfer also happens when we using the some consumable electrode. Then if heat concentration is very high, there is a evaporation of the material also happens if the peak temperature is very high, or maybe if the maximum temperature, this is the evaporation temperature of the material. So, evaporation of the material will also occur at this point of view. So, that molten droplet transfer from the some consumable electrode, that actually influence on the weld pool in the sense that molten when there is a continuous adding of the molten pool, that continuous adding to the mass in the domain, solution domain, and that actually influence the material flow within the small weld pool. And of course, with the advancement of this consumable electrode, the subsequently solidification also happen and heat lost due to the convection and radiation from the surface or inside the domain, just at the solid liquid interface towards the solid domain, the heat is conducted away, and that finally when conducted away, and finally when it is come into and on the surface, there is a heat lost by the convection and radiation in that mode. So, this all these physical aspects actually involved in the welding process. So, considering all these physical activities involved here and representation of this in some mathematical model, it becomes more complex and complex. So, we can look into the one by one. So, first we will look into the thermal aspect, then metal flow aspect, and finally, we will look into the solidification, that means residual stress or distortion aspect. Now, if we look into that, focus on the specific to the weld pool, what are the different driving forces is acting, because if we know, of course, there is a heat conduction within the molten pool, at the same time at the outside of the solid liquid interface, but at the same time there is a flow of the molten material. And if you see, if there is a arc welding process, it is not necessary the surface will be the flat which was the initial, because there is a arc and there is a acting of the arc pressure on the top surface. So, that changes the free surface profile. So, free surface can be in having some having some curvature. So, it may not be flat. So, at the same time evaporation, and on the when there is a interaction between the arc and the molten pool. So, Marangoni shear stress is actually in the on the surface, that means surface tension force actually act when the two different medium come into contact, the liquid and gaseous medium. So, at the interface definitely there some Marangoni shear stress. So, that Marangoni shear stress basically, or maybe in the surface tension force, actually one of the driving force that control the magnitude and the direction of the material flow within the small oil pool. And at the same time, since in case of arc welding, since there is a flow of the current involved, so that will create some electromagnetic field within the oil pool. So, electromagnetic field also having some influence on the material flow, and of course, buoyancy force is also acts, and that buoyancy force and electromagnetic force, actually these two are the body force. That means, these two body force is responsible, and that actually influence the material flow pattern within the oil pool. What just outside the oil pool, there is a conductive heat transfer also occurs, and with the after some time, that means when the heat source moves from one point to other point, then previous zone actually solidify. So, after solidification, there is some microstructural changes also happen, that is different from the base material structure. So, these microstructural changes also happens within the molten pool, because that depends on the solidification behavior of this material, but at the same time there is a microstructural changes also happens in the heat affected zone. That depends, that heat affected zone, we can say that the solid state phase transformation also happens within the heat affected zone, and then structure may be different from the solidified zone, or maybe from the with respect to the base material. So, this all phenomena happens during the welding process, but at the same time there is some convection and radiation heat loss from the outer boundary. So, this is the typical physical aspects or physical phenomena actually happens in the welding process. Now, we will try to look into how all these aspects can be represented in the mathematical sense. Now, after fusion welding, maybe in the physical aspect of solid state welding, we can see that in the solid state welding process, normally the heat is generated by frictional force, or frictional heat generation mainly happens instead of arc or laser source in case of fusion welding process. So, in solid state welding, mainly along with the frictional heat generation, there is a stirring action also happens that we observe in the friction state welding process. So, that plasticization of materials also happens in this process. Then, but in this case, the solid state welding process, the temperature is limited below the melting point temperature. So, in this case, the temperature is well below the melting point temperature. So, there is no problem of the that is related to solidification, it happens in case of fusion welding process. Then, since the maximum temperature is below the melting point temperature of this material during the solid state welding process. So, here the solid state phase transformation is mainly happens, and finally, the same heat conduct that we can see the heat transfer also happens, that we normally found out through the by solving the heat conduction equation, and of course, here we can model the material flow also. But in this case, material flow is the maybe we can consider solid state welding process mostly the viscoplastic nature of the material, and based on that we can model the material flow, and most of the cases we can find out the distribution of the strain rate in case of the solid state welding process. So, finally, like fusion welding process, but there is some residual stress generation, but distortion level in solid state welding process is normally very less as compared to the fusion welding process. Of course, these are the typical advantage of the solid state welding process, or difference I can say as compared to the fusion welding process. Now, analysis of the heat flow, there are what are the governing equation or any constitutive equation we can use for the analysis of the heat flow, or for the to estimate the temperature distribution within the domain of interest. So, in case of welding process, the governing equation, we consider the heat conduction equation, Fourier's law of heat conduction equation, we can use it, and we can solve for the temperature in this case. Of course, a non-Fourier heat conduction is also important, but non-Fourier heat conduction we just apply in very specific cases, specifically in case of the ultra short pulse laser welding process. So, in that case there is a need of solution of the non-Fourier heat conduction equation. We will see the difference between the Fourier heat conduction and non-Fourier heat conduction in terms of the differential equation. Then next part is that although the governing equation heat conduction is we can solve, but how to represent the heat source. There is a definitely the representation of heat source normally happens in normally we represent in the mathematical way, assuming that it is a point heat source, assuming that it can be a line heat source. That means energy transport through that means it is a string line of the source, and then either it can be distributed over a certain area or distributed over volume. So, that is the distributed heat source. So, these are the typical division of the different nature of the heat source that we represent mathematically. But apart from the heat conduction equation, it is also necessary to find out the sometimes we solve the equation of the heat transfer and the fluid flow if we more precisely estimate the temperature distribution, because the material flow within the small oil pool that actually influence the heat transfer or influence the temperature distribution. For example, heat conduction equation, here we generally solve only the heat conduction equation, that means without consideration of the material flow within the oil pool. Also approximately we can get some solution, and that solution is also acceptable, but if we try to incorporate the effect of the material flow which actually happens in the fusion welding process, in that case we can improve the results at a lot, or more accurately we can estimate the temperature distribution. Of course, at the same time the fluid flow, that means velocity distribution within the small oil pool, and we can explain the different phenomena associated with the fluid flow in the oil pool. But in this case we normally solve the conservation of mass, momentum or energy equation. So, in this case the energy transport equation we can, if energy equation what we consider in case of the heat conduction equation, but in this case the extra term is the energy transport due to the flow field of the material. So, that term is added in this case. So, then that we necessary to solve along with the heat conduction equation in this case. And then for the material flow analysis, you can say the mass momentum equation, or for momentum equation we generally solve the Navier-Stokes equation to estimate the velocity field within the small oil pool. Of course, as compared to the heat conduction and this heat transfer and fluid flow, transport equation is computationally more costly, that means computational time will be more in this case as compared to the heat conduction equation. Then another aspect is that in case of heat conduction, or in case of the try to estimate the temperature distribution with the oil pool. So, in sometimes in case of laser welding and of course electron beam welding, and sometimes in case of plasma welding also there is a formation of the keyhole formation may happen. So, in this case when there is a keyhole formation, that keyhole is a domain within the oil pool, and when practically when we use the very high concentrated laser, high power density is very high, that actually try to create the keyhole formation. So, that in the keyhole formation there is a evolution of the liquid vapor interface. So, over time considering the effect of the interfacial phenomena like evaporation, homogeneous boiling and multiple liquefaction taking into account, and we can predict we can develop the geometrical model of the keyhole. So, that means we can predict the size of the keyhole in case of the laser welding process. So, otherwise apart from the keyhole, if there is a conduction mode laser welding process, so only heat conduction equation or maybe heat transfer fluid flow equation is sufficient to predict the temperature distribution. But if when you use the very high concentrated heat in specifically in laser welding or electron beam welding condition, in this case there is a formation of the keyhole. So, we need to consider the keyhole effect, and then we can improve the simulation process. Then simulation means we can improve the temperature distribution process in this case. So, these are the typical aspects for the analysis of the heat flow. Now, we come to that point. Cooling rate is very significant parameter, and we will see in the solidification process this cooling rate is very significant important, because by looking into the cooling rate or using the information available in the phase transformation diagram, for example, TTT diagram, CCT diagram and continuous, this type of phase transformation diagram, we can estimate that if with respect to the typical cooling rate and what should be the expected microstructure in a weld joint. So, that is why it is necessary to estimate the cooling rate during the welding process. Just before cooling rate means we understand the rate of change of temperature, that means change of temperature with respect to time. So, that is the very simplified way to represent the cooling rate, but in welding process how we can estimate in the cooling rate, just let us look into these two figures. So, first figure actually represent the time versus a temperature diagram at different location in a weld joint. So, for example, if we take one specific metallic plate and we start welding from, that means we are applying the heat source from one point and gradually the heat source is moving, but before doing that we can fix certain location into the workpiece. So, that fixed location we can measure the temperature, that means that fixed location the temperature will vary with respect to time, and that depends on the at what speed the welding source is moving from one point to another point. So, that means it is like that only. So, for a fixed location this the curve represents the time versus temperatures cycle. So, if we have this information, and practically this information we generally capture using the by putting some thermocouple in the workpiece, and then we capture the using the data logger we can measure the data time versus temperature, and if we plot it we will getting the typical measure. So, first if we see there is an increment of the temperature, we can say this is the heating phase, that means one specific point there is a gradual increment of the temperature, that means in that location if the heat source is going nearer to that point, then exactly the nearest point with that point with respect to the heat source. So, at this point it will achieve the maximum temperature, and then if we further move the heat source, then gradually there is a decrement of the temperature, because heat source is away from that fixed location. So, temperature will decrease. So, that second phase when temperature will decrease, we can say this is a cooling phase. So, during the decrement of the temperature, so that basically the slope here, the dt by dt, that means change of temperature with respect to time, graphically it represents the slope on this curve. So, that slope actually represents the rate of cooling. What if we convert this typical time versus temperature curve in terms of the cooling rate dt by dt, and with respect to welding time, we can find out that there is a cooling rate actually varies. So, that means slope is not constant, there is a continuous variation of the cooling rate, that depends what number of points we are considering, or gap of the points we are between the 2 points we are considering here. So, but this is the typical cooling rate versus welding time that time. So, there is a variable cooling rate. Now, to this variable cooling rate, it is very difficult to predict the actual microstructure and to link with the cooling rate. So, to avoid this kind of situation, we can represent the cooling rate in the that means we can say the average cooling rate value. So, average cooling rate value, if you see the expression of the average cooling rate value, T beta minus T alpha divided by T beta by alpha. That means, here T beta and T alpha is the two different phase that in the structure microstructure different phase. So, different phase the change of the phase happen from one temperature to the other temperature, that gap phase change temperature of the beta phase, what is the temperature, and corresponds to the what is the phase change temperature corresponding to the alpha phase. So, that means over the duration of this phase change temperature and what is the corresponding time is required, that ratio we can represent in the average cooling rate. So, in that way we can this average cooling rate estimation, it gets some information that over a duration of the time what is the duration of the time is required to change one phase to another phase, and with in terms of their temperature. So, that is why if we do that, then we can find out the average cooling rate, and then we can more precisely predict the or maybe link this average cooling rate with respect to the typical microstructure. We will discuss further on this analysis that how we can estimate the cooling rate also. Now, I come to that point Of course, there are different way to represent the heat source. So, that here I am trying to look into that models of the welding heat source, that is one of the very important aspect in the computational welding mechanics. So, to understand that how to represent the heat source in here. But if you look into that, nature or type of the heat source can be different, that means it can be practically the heat source can be from the arc, heat can be come from the laser also, heat source can be electron beam, it can be resistant. So, all the different type and nature of the heat source are different, but mathematical representation is like that. We can represent the heat source starting from the point, line and distribution. Looking into that, looking into the nature of the heat source. For example, it is a laser actually focus in a very small area. So, it is better to represent the laser source as a line heat source. So, that means over the length of the line, it is a string of the energy that acts as a source of the heat, and that source of the heat we finally, if we apply on the workpiece surface, that will generate the amount of the heat. So, that is one example. For example, arc. So, it is better, it is not a good idea to represent the arc, because arc heat source is more distributed. That means, it is not concentrated in very small zone like laser. So, arc can be represented as a distributed heat source. So, like that, it is a representation, mathematical representation from the very simple point to the very more realistic. For example, point and line heat source, it is not actually realistic, but realistic is the representation of heat source is more distributed, and that distribution may happen over the surface, or distribution can be considered over the volume also. So, that distributed heat source, two nature, either surface heat source or volumetric heat source, that is the more realistic heat source. Then surface heat source, and that normally follow the distribution over a surface, it is follow the Gaussian distribution. Normally Gaussian distribution means at the center point the heat intensity is maximum, and it gradually decreasing to the boundary of the well defined zone. Then volumetric heat source, but volumetric, when you try to represent the volumetric heat source, when we can assume the as a certain time there is a heat that a certain predefined volume can be represented as the source of the energy. But when these two aspects are involved in the representation of the volumetric heat source, one is the geometric shape. Geometric shape, that means what way we generally represent the volume of the volumetric source. So, that normally represents in the regular geometric shape. For example, ellipsoidal, double ellipsoidal, that kind of, or conical, that is the regular geometric shape. Sometimes we use this to define the geometric shape of the volumetric. And then second point is the distribution, that means over this geometric shape how the energy is distributed. That means, it is not necessary that throughout the volume the uniform distribution it follow. That means, throughout the volume it is better to represent the volume at one specific center, that means one specific center point the heat intensity will be the maximum, and then gradually it can decreasing. That type of that means that Gaussian distribution most of the cases we follow, but of course, other type of the distribution can also be followed. Then another aspect is the two representation of the heat source, that whether the nature of the heat source or representation of the heat source is symmetric or non-symmetric, and what way we can decide whether it is symmetric or non-symmetric. For example, in case of spot welding, this heat source can be represented as in a symmetric nature, but in case of linear welding, that means when there is a movement of the heat source, when there is a movement of the heat source with respect to certain plane, the heat source is non-symmetric. Either in that non-symmetry can be represented either in geometry or can be represented in either distribution or both. In that way we can represent the different type of the heat source. So, we will discuss more on that. Here models of the heat source in welding terminology, or maybe in the in case of welding process, we can find out the different type of the heat source model developed so far until is developing, and the other type of the heat source models in case of welding process. First is the circular disc shape heat source model, then ellipsoidal heat source model, double ellipsoidal heat source model, quadruple ellipsoidal heat source model, conical heat source model, egg configuration heat source model, hybrid heat source model. So, these are the typical names that we use in case of the welding simulation, that different type of the heat source model. Of course, there is much more, but here I am trying to make you understand that what way we can represent the heat source. So, let us look into this first figure. So, here on the xy plane we consider the simply one circle. So, that means on this circle, so this type of, that means we assume that there is a surface heat flux. So, that means heat in terms of the flux, it is intensity is the one specific point at the center point, at the origin point, the intensity is the maximum, and then it is distributed throughout this area, surface area. So, at the center point it is the maximum, intensity is maximum, and then gradually if you go towards the periphery of the circle, so gradually it is, or boundary, gradually it is decreasing. So, these are this way we represent the Gaussian distribution of the heat source and over the surface, and that this type of heat source normally we use in case of the spot welding. That means, when there is no movement of the heat source. So, that means for the stationary heat source, typical we use the surface heat source. But this surface heat source is limited when the sheet thickness is very small, or maybe heat intensity is very small. So, surface heat flux or surface heat source model is more representative. But if the intensity is very high, then means in that case we consider generally the not surface heat source model, that we can say volumetric heat source. In that case we represent the volumetric heat source, that means the heat is distributed over the volume. For example, if on the top surface it is on the circular shape, then it can be like that on the along the z axis and on the x z plane, we can represent this as a kind of ellipse, part of the ellipse. So, that means over the surface the circular, but at the depth direction, if you in the x z plane, it can be like ellipse. So, therefore, if we represent the in case of spot welding, but if heat intensity is very high, then we can use the ellipsoidal heat source model. This is one kind of the volumetric heat source model. So, that ellipsoidal heat source model is the first and second figure that represents the ellipsoidal heat source model. But there is other things, that is the case for the spot welding. But if the heat source moves, then what way we can represent the heat source? That means, in this case, since the heat source is moving in, or maybe in practical arc or laser is moving on specific direction. So, in that case it is not necessary with respect to the one plane, it looks like exactly the symmetric nature. So, here brings the non-symmetric nature of the heat distribution as well as the geometric shape of the weld pool, which since there is some finite amount of the velocity one specific direction. So, in that case, then that means in that case it is called generally linear welding. So, in case of the linear welding, then normally we use the double ellipsoidal heat source model. Of course, we can use the volumetric heat source model, but the volumetric heat source model just merging the part of the two ellipsoidal heat source model. So, then it becomes the double ellipsoidal model. Here you can see that third figure. So, with respect to the y axis, the front side is the one ellipsoidal and the back side we can with the another ellipsoidal, but such that exactly the one parameter is the same in this case, and we can consider that merging the two ellipsoidal and we can create the double ellipsoidal heat source model. That is the better representation of the moving heat source for the high intensity laser or electron beam or some other high intensity arc also. So, with in that case this is the representation of the volumetric heat source by a by merging the two ellipsoidal. So, that is called double ellipsoidal heat source model. Then comes into the picture the quadruple ellipsoidal heat source model. So, quadruple ellipsoidal heat source model, it is simply nothing but instead of the 2 ellipsoidal, here we can use the 4 ellipsoidal heat source and we can merge it this geometric shape to take into account the 2 nonlinear non-symmetric nature. One non-symmetric nature is that due to the welding movement in one direction, other is will be the due to the 2 different material when you try to join 2 different material. So, 2 different material, the energy absorption or will be different because of their thermophysical properties are also different. So, in that case, so to account all this non-symmetric nature, the energy distribution for the material A and material B at the same time due to the linear movement in one direction, we can merge the 4 ellipsoidal together and we can create this quadruple ellipsoidal heat source model. Of course, sometimes people use the conical heat source model, because conical heat source model is the in this case when the temperature gradient is very high along the depth direction, maybe specifically for laser welding process. So, because heat intensity is very high, so in that case we can use the represents the geometric shape of the heat source as a conical, and we can follow the other distribution also. And recently there is a development of the egg configuration heat source module discussed, that the looking into the distribution, simply modifying the ellipsoidal heat source model, we can we can develop the egg configuration heat source model. And sometimes people use the hybrid heat source model, that means by combining the conical and the ellipsoidal, certain part will be the ellipsoidal source and certain part will be the conical heat source to present the complex nature of the welding process, or maybe in hybrid welding process the representation of heat source, people normally use the hybrid heat source model by combining the 2 different regular geometric shape and develop the heat source model for in that case. But one point is that there is a another type of the heat source model, that is called the adaptive volumetric heat source model. So, adaptive volumetric heat source model, this is introduced in the sense that there is a all these heat source model, when you try to apply in simulation of the welding process, we need to predefine all the parameters. For example, geometric parameters of the ellipsoidal source, or maybe geometric for ellipsoidal, or geometric parameters for the conical, geometric parameters for the double ellipsoidal. So, to avoid these things, if we continuously adapt with respect to the analysis time step or with respect to the load step, if we continuously adapt the shape and size from the estimation of the temperature from profile, that means estimation of the oil pool profile, and that directly map continuously with the geometric shape, and in that way it is possible to develop the adaptive nature of the heat source. So, in that case it is not necessary to predefine all the geometric parameters in this case. We will discuss in details the adaptive volumetric heat source. Now, we start from the models of the heat source, but just look into that disc type of heat source. Here you can see that top figure, it is a representation of the arc. Normally we can see the end of the flame happens over a certain boundary with respect to the center, and this follows generally typical Gaussian distribution. Now, this heat distribution, in mathematical representation of the heat distribution, we can use this equation, the QR, that means Q, the heat intensity at a radial distance r equal to Q max. Q max means at r equal to 0, what is the maximum intensity, and how it varies with respect to the maximum value. It starts from the maximum value and gradually decreasing with the exponential way. So, exp exponential way, and that minus c into r square. C is the distribution coefficients. Actually, the c, by varying the value of the c, we can represent the distribution whether it is very stiff or whether it is very flat, that actually decided by this parameter distribution coefficient c. So, this is the typical representation of the surface heat flux that we can follow, we can see in the welding process. Now, there is another representation, that is the double ellipsoidal heat source model. So, here also if we see the figure, that at the there is a geometric parameter of the double ellipsoid is like that, Cf and Cr, that brings the distribution of the because temperature gradient or maybe energy deposit in the front and the back side of the will may be different because of the velocity in one direction, and then A maybe another dimension of the ellipsoidal and depth represented by the B. So, A, B, C, F and C are all geometric parameters of the double ellipsoidal heat source. And then if we know the geometric parameters, or if we can define the geometric parameters, we can represent the distribution or heat flux, that heat flux distribution of the heat flux over the volume can be represented by the these two equations, first equation and second equation. But different of these two equations is that we can non-even distribution of the energy in the front part of the ellipsoid and the back part of the ellipsoid can be taken care of by these two factors FF and FR. These two fraction actually brings the difference in the non-uniform energy distribution in the front and the back side of the ellipsoidal double ellipsoidal heat source model. So, here if you see that QF as a function of x, y, z and time t, we can represent this thing, and here Q, capital Q, it represents the actual amount of the heat is applied to this. So, this Q can be estimated that what is the effective amount of the energy is transferred to the workpiece from the laser, either from the laser or from the arc. So, we will see how to estimate this key. Here how to represent the heat source is that this is the one typical conical heat source model. Here you can see the we can consider the truncated cone geometric shape, and on the top surface the distribution can follow the Gaussian distribution, that means at the center it is a maximum Q0 and gradually decreasing. And then typical estimation that flux density distribution can be formed in this way. The P basically is the laser power efficiency and all geometric parameters E, radial distance R, Z E and Z I are geometric parameters of the cone with respect to the certain coordinate system. And then if we define all these parameters, we can easily define the conical heat source model also. Here you can see the quadruple ellipsoidal heat source model. So, here if you look into that figure, there is the merge of the 4 ellipsoidal. Here we can see the 1, 2, 3, 4. So, with respect to the x axis, if we consider the x axis, upper side is the first material, maybe one material, and the other side is the another material, second material. So, that since the two materials having variation in the thermophysical properties, so therefore, non-symmetry energy distribution will occur between these two metals. But in term what way, since the non-symmetry energy distribution, then this is the one way to represent the heat source or to bring the difference in the heat source model. So, that is why this dimension of the ellipsoidal, the parameters in the first material, one material and the other material will be different in this case. So, non-symmetry energy distribution due to one reason is that two different material, and another reason is that there is another moving heat source. So, when you want to take care of the moving heat source, then we can consider the non-symmetry with respect to the y axis. So, non-symmetry with respect to the y axis as well as non-symmetry with respect to the x axis for the two different materials. So, then we merge the 4 ellipsoidal part of the ellipsoid here 1, 2, 3, 4, and we can make this ellipsoidal heat source, quadruple ellipsoidal heat source model. So, of course, because here you can see the double ellipsoidal heat source model only accounts the non-symmetry in terms of the moving heat source only. Double ellipsoidal model is here, the double ellipsoidal model we can simply extend in terms of the quadruple ellipsoidal heat source model to accounts the non-symmetry energy distribution and simply contents of the 4 parts of the ellipsoids. And then, but this one thing we have followed here, that depth of penetration, that means depth of penetration remain the same, and of course maintain the C1 continuity. That means when you merging this thing, the 4 ellipsoids, in this case that the slope at this point is there is the continuous slope at this point. So, there is no mismatch in the slope as well as continuity is also there. So, that is why we are maintaining here the C1 continuity to develop this heat source model. Now, adaptive, I have tried to represent the adaptive heat source model we use in the welding process. So, if we see the in case of spot welding process, there is a definition of the that means volumetric heat source can be represented by defining the by assuming the equation of the or assuming the geometric shape of the ellipsoid. So, here that ellipsoid the once we define the ellipsoid, but that parameters geometric parameters of the ellipsoid can be vary with respect to time or can be vary with respect to the load step. And we have already mentioned that we are doing the adaptive heat source model because the all other heat source model here it is necessary to predefine the heat source parameter. So, before start of the simulation for the temperature distribution, we need to define all the geometric parameters of the heat source, and then we can use this volumetric heat source for the temperature simulation, but in adaptive case it is not necessary to predefine. So, in that sense it is advantageous or maybe one development happens in case of the simulation of the welding process. So, in adaptive welding process we can use the same distribution equation what we consider in the ellipsoidal or double ellipsoidal heat source model, but only thing is that there is a continuous changing of these geometric parameters with respect to time if we use the transient analysis or with respect to the load step if we do some steady state analysis. So, definitely this adaptive volumetric heat source should follow some strategy for the implementation of the any finite element based analysis. In case of adaptive volumetric heat source, in case of in fusion welding, here you can see specifically when we try to apply in case of steady state analysis, because steady state analysis the development of temperature in one specific point we can observe, but it is not a function of time. So, then how to adapt, how to change these parameters, that means how to change these heat source parameters. So, here we can see that the distribution equation source is the heat source changes, that means heat source, the distribution is over the space, there is no time function here, and we see that double ellipsoidal geometric parameters, that means length, width and penetration A, B, C, the length, these things we are simply mapping a length on this with the geometric size of the volumetric heat source. Now, if you look into that figure, there is a continuous development of the, that means updation of the the different parameters. So, we see the double ellipsoidal heat source model A, B, C, and then these are the three parameter, or A is basically A1 plus A2, that means due to the linear movement A1 and A2, and other two parameters B and C. So, all these parameters evolve with respect to the ramped up power, that means normally we do the steady state analysis in the during numerical simulation, not directly putting the whole power in a single step, rather total power we can divide into number of steps, that means we can divide in, that is called the load step. So, each and every load step we can update the value of the geometric parameters of the double ellipsoidal heat source, and then once updating, then there is a gradual changing of the volumetric heat source. So, that means with this that updating is happens with respect to the ramped up power here as compared to the transient analysis, because in transient analysis this mapping or changes of these geometric parameters actually happens with respect to time, that is the difference. So, in this way we can implement the adaptive volumetric heat source. We can show some simulation also, that adaptive volumetric heat source in steady state situation. Here you can see the in the first figure actually we actually apply the 25% of the effective load. That means we can say, suppose our total power in the steady state welding process is 1 kilowatt. So, therefore, after application of the 250 watt power, this is the typical size of the weld pool. Here you can find out the weld pool, that means red color is mainly represents the molten pool zone, and remaining other colors actually represented depending upon the phase that heat affected zone, just looking into the different phase transformation temperature here. So, then when the 100% effective load is happening, then that means we completely application of the 1 kilowatt power, then there is a this represents the that shape or size of the oil pool. So, which is different from the first figure. So, this way we can see there is a continuous development of the oil pool, but during this continuous development of the oil pool with respect to the ramped up power, here each and every step there is a updating of the volumetric geometric parameters of the volumetric heat source. We can see from the figure also that width and the effective load step there is a gradual increment of the effective load steps and there is a variation of the width. So, that means from the very beginning the 25% effective load there is a small width and gradually increasing, and almost up certain time on the 100% load it reach the steady state situation, and that is actually implemented using the adaptive volumetric heat source. But one point like to mention that this adaptive nature of the heat source is independent of the geometric shape and size. This can be implemented by assuming the any other geometric shape and size of the volumetric heat source. For example, not only limited to only the ellipsoidal, double ellipsoidal heat source, we can assume the any other geometric shape of the volumetric heat source, and the similar fashion we can apply the concept of the adaptive volumetric heat source for the simulation of the welding process. So, here we can see the adaptive volumetric heat source in the transient state. So, transient state also in case of specific welding process, and we assume the ellipsoidal volumetric heat source, the geometric shape the volumetric is assumed as a ellipsoid. So, here you see 0.2 second there is a development of some oil pool developed, or gradually it is increasing, and when it reaches to the 0.5 second the oil pool size is bigger. So, throughout this time step, the different time step, or maybe we can say that at different time there is a updating of the geometric parameters, and we can see that from the figure that penetration and the on time, that means laser on time, continuously we give putting the laser on time, there is a gradual development of the oil penetration, that means 0.2 there is a less amount of the penetration, but when it is the 0.5 second the penetration becomes very big. So, there is a continuous development of the oil pool, and we are doing the simulation just simply this growth development of the oil pool. That means, we measure at any step at any point of time what is the size of the oil pool, and that size we simply mapping with the size of the volumetric heat source. There is another type of the heat source that is called development happens, that is called egg configuration heat source model. Here you can see the equation is basically we use the ellipsoidal, when you try to develop the ellipsoidal heat source model we use this equation, but if we use just multiplying the factor T y any functional form, we can modify the equation a different way. So, egg configuration heat source model just simply modifying the ellipsoidal equation and by introducing some functional form in this way, that means x square and z square, that is modified by the T y, that means that is functional form as a function of y here. Then we can develop the different shape, we can generate the different shape of the different geometric shape. So, that is called typically called the egg configuration heat source model. So, it looks like an oval shape, or maybe you can say the egg shape. So, if you see this figure, that if we change this parameter, because T y 1 by we consider the one that this functional form is the 1 by m y plus m square y square plus 1. So, here by simply changing the value of m we can generate the different shape. Let us see that we here different shape can be generated, or we need to optimize what may be typical value of the m such that we can use this geometric shape for the oil pool simulation. So, in this case if T y equal to 1, that means T y equal to 1, it is the simply representation of the equation of an ellipsoid, that means that is equal to, if T y equal to 1, that it becomes equivalent to the ellipsoidal heat source model. So, here you can see the difference between the ellipse and the egg shape. So, in certain ellipse is a very symmetric with respect to this thing, and most of the cases we merge the two ellipsoid, and we generally generate a double ellipsoidal heat source model merging the two ellipsoid. So, in this case double ellipsoidal heat source model, actually the number of parameters are more, but we can reduce this parameter by simply looking into this concept by checking the geometric shape that looks like an oval shape or looks like an egg shape, simply the modifying the equation of the open ellipsoid. So, this can be incorporated in the weld pool modeling of this thing, that is the one of the modeling approach where we can apply the A configuration heat source model.